All right, hello everyone. Welcome to today's presentation. My name is Savannah Hinchin, and I'm a technical sales rep at EOS Remediation. Today's topic is consideration for use of passive no-purge groundwater sampling. Our speaker today is Mr. Sandy Britt, President and Principal Hydrogeologist with ProHydro Inc. Mr. Britt has a bachelor's and master's degrees in geology from the University of Rochester and University of Southern California. He has worked as a consultant in water resources and environmental roles as a regulator at the California Department of Toxic Substance Control and currently manages development and sales for ProHydro Inc., primarily for the SNAP sampler groundwater monitoring product line. Mr. Britt also conducts research for the Department of Defense through their SERDP and ESTCP programs, including basic research on well flow dynamics and representativeness of various sampling methods. Sandy helped develop the ITRC Passive Sampling Guide as well as the ASTM Standard on Passive Groundwater Sampling. Sandy's discussion today will explain some background on passive groundwater sampling, how wells function in the subsurface, as well as details about available sampling approaches. So before we get started, I'd like to share a little bit about EOS Remediation and what we do. EOS is the original developer of the emulsified oil technology for in-situ bioremediation. We are located in Raleigh, North Carolina, and have been in business since 2002. Few updates I'll briefly mention is the next conference we'll be attending is AEHS in San Diego. Stop by the booth on March 23rd through the 26th and say hi to Bill. And Brad Elkins will be at the remediation workshops in Sacramento, California on March 24th and Oakland, California on March 25th. For more information about that, go ahead and go to remediationworkshop.com. So now I will pass the torch over to Sandy and let him start his presentation.
Thank you so much, Savannah. I'm going to go ahead and pull up my PowerPoint presentation. Give me 1 second to go ahead and set that up and make my parts go where they are so I can look at it properly. Thank you so much. EOS has graciously invited me to give a presentation on passive groundwater sampling. I'm going to spend some time talking about background information on passive sampling and why passive sampling works. Probably half the talk is actually going to be about how wells work, which is really sort of near and dear to my heart. I've been thinking about this for 20 years, and as a former regulator at the Department of Toxic Substances Control, I did some work there trying to understand some things that I couldn't find in the literature, and I'll kind of explain some of that probably in the first third to half of the presentation, and then I'll talk some about passive sampling and how it actually is implemented in the field and what some of the results look like. So I'll just go ahead with that. Okay, so my outline, basically I'm going to talk about how a well works. It's dark down there and we don't always know what's going on until 3 weeks later when we get lab results back. And if things are a little confusing, then we don't really know what happened most of the time. What happens in the well between sampling events is 99.9% of the action happening in the well. And information I thought was fascinating, especially the further I explored it. There are interesting things that happen with well flow dynamics, mixing, and flow weighting that actually occur in a well, even while we're not doing anything to it. It's sort of a fallacy to think that a well is stagnant. It's really just a giant pore space in the subsurface, and water will flow through that giant pore space, and I'll explain some of the dynamics of that during the course of the presentation. Pumping also is a way to collect samples, obviously. Most people have been doing that since the beginning of groundwater sampling for contamination investigations. It's dark down there for that, too. We don't really see what's happening. some of the research that I did through SERDP and ESTCP highlighted that aspect, and we did some modeling, and there's some cool graphics that I'm going to show you that illustrate how water flows in a well.
Hey, Sandy.
Cool. Yeah.
We have just a couple brief comments about we're having a hard time hearing you. I don't know if you can speak a little bit louder into the microphone.
Okay, I'll try. I'll put the microphone a little closer. Hopefully this will be better. Try not to yell too much for people who can't hear me, but I'll go ahead and finish the outline. And if please speak up if it becomes if that problem continues as we go forward. Appreciate that. Thanks a lot, Savannah.
No worries.
Okay. We'll talk about passive sampling methods, the different approaches, how passive sampling can be used to collect representative samples from groundwater monitoring wells. Talk about how to choose the different methods, about data quality and differences between the methods. Also talk about cost. I mean, cost is really oftentimes the big driver for seeking an alternative sampling method. Then we'll talk about resources. There are several of them out there. Numerous test studies have been done to compare different passive sampling methods. The picture here is a picture of me at a contaminated site near Los Angeles holding a snap sampler, which is the device that my company developed for passive groundwater sampling. I'll spend a little bit of time talking about that. We're the company who sells that, so apologize in advance for spending a little bit of time on that, but I thought it's important to introduce it. It's not going to be overwhelming amount of information on the snap sampler. Groundwater sampling black box. Like I said before, the well itself is it's dark. It gets dark within a couple feet of ground surface, and so we don't really know what's going on. Why do we purge? Well, 30 or 40 years ago, we didn't know what was going on, and the safe thing to do is to purge all the water out of there so that you can be assured that there's new formation water that you're sampling. Regulatory requirements developed out of that, but pretty soon after that became established, people thought, you know what, this is really a lot of work, generates a lot of waste, and maybe isn't the best way to do it. There's a lot of turbidity generated and a lot of work that goes into collecting those kind of samples with multiple well volumes being purged. So low flow sampling was developed to limit that volume and also improve data quality. So regulatory requirements have changed over time, and it hasn't been fixed the whole way through the groundwater sampling regime or history. But ultimately, the idea is to generate samples that are representative. And so guidance has changed over the years to reflect new technologies. Passive sampling is a series of new technologies that take advantage of some of the physical aspects of groundwater flow and monitoring wells, and in many cases can allow you to collect representative samples. But we have a tradition. Everyone's been purge sampling for a very long time, and it's easy to fall back into that tradition and not want to change. Hopefully I can explain some things today that will maybe lead you to thinking that maybe there are other alternatives that will allow you to get just as good samples without nearly as much work. We do know how wells work. We do know in large part that we know that hydraulics controls flow. But for a long time, people have been looking at water flow in screen zones of wells. And really the differential between the old-fashioned way of thinking you had to purge multiple well volumes to clear the well out really only applied to the water column above the screen. People really understood that the screen zone itself always would flow through, but because it's dark down there, we didn't really understand it. So there were some researchers that wanted to avoid this whole purging process, including the low-flow camp and then later on the passive sampling camp. And so what happens in the well is something that was less understood, and there was concern about how contaminants would enter a well and how they would behave in there. But I think that there was not too much debate about the screen zone of the well itself. And if you look at the quote that I have there for the ASTM standard, just read part of that quickly. It explains that researchers have long noticed and known that water does move through the well screen, and that water in the well screen is representative of the formation surrounding the screen. That's from the ASTM standard for low flow sampling. That's in revision right now, but I think that it reflects a consensus at that time that low flow also represents or relies on flow in the well. You're not purging multiple well volumes with low flow, so you're relying on at least some of the casing water or the screen zone water being representative of the formation itself. Okay, so in that well screen, what could possibly happen? Basically, there are 4 different scenarios that could happen. You could have water contaminants and uncontaminated water just flow straight across the well, like is pictured in slide number 1. Or maybe there's a little bit of diffusive or dispersive mixing as that contaminant enters the well in number 2. Or you could have complete mixing as shown in number 3. Or maybe you could have a density-driven flow as shown in 4. I mentioned before that I did some research when I was at the Department of Toxic Substances Control. What I convinced a receptive supervisor to allow me to do a little bit of an experiment. I got some funding from the Air Force to pay for my time and also some of the equipment. It wasn't too much money to build the equipment. It was only about $600 to build this sand tank that I have here, and to test it and to see what happens as a contaminant or a proxy for a contaminant. In this case, rhodamine dye diluted in water, and how that enters into a well and how it behaves once it's in the well. So in this tank example, let me get my little pointer, a little spotlight. So inside the well here, that's a 4-inch screen, and this is a sand body to the left and to the right of the sand tank. These 2 buckets are used to maintain head above the level of the water in the tank. And then we flew, I made water flow through it at a slow flow rate approximating groundwater flow rate. All right. Okay. Savannah, can you see my arrow? If I can use my arrow, it might be a little easier. I don't know if Savannah's still here.
Yes.
Anyway, these 2 buckets on the right. Okay, thank you.
We're still having some sound problems, though.
Boy, I'm really speaking right into the phone. I'll try to speak up as best I can. Is that a little bit better?
It works for me. We can hear you fine, but it just some people have said that it's just difficult to hear. So
okay, I'll do my best to speak up as well as I can, and so that people who have quiet phones or whatever can hear. Okay, so the tank here that was built, a rhodamine dye was added and allowed to flow at groundwater flow velocities about 1/2 foot per day. And so the next slide, there we go. So this is just a close-up with, you can see the dye entering the tank to the left, and you can sort of see it's a little pink there where the dye is inserted. And then over a long period of time, very slow flow rates, in this case 21 hours, the dye enters the well and mixes in sort of both directions vertically. The flow rate was controlled with just gravity feed, or about a drop every 3 or 4 seconds was actually equivalent to 1/2 foot per day flow velocity. The physical model here was put together so that we could create that flow velocity, and we tried as best I can to get the density to be as close to neutral as possible. I mentioned that, and so in this study, you'll see in the next couple slides that I have a time series that show it. But right now, I'm going to show a model that we created in our SERDP project a few years later to mimic this. And I hope that you guys can see my my video here, and we'll show that the numerical model was designed to mimic the tank with a density, in this example, a density greater than 1. In this case, about 3 times 10 to the minus 7, so about 300 parts per billion. A little bit heavier than the neutral tank, and you can see that because all the dye seems to stay at the low end of the tank. I also want you to notice this little inhibitor, this mixing inhibitor that's placed in here. In a slide or two, I'm going to show an example of how that is used in the field to illustrate a way to isolate contamination zones in the well. So this is the time series of the physical tank showing many hours of dye entry and mixing, and over about a 4-day period it comes to what seems to be a dynamic equilibrium, where the dye concentration actually averages across the well where the range of concentration goes from about 33% of the full dye concentration up to about 40% in the center and down again to about 35%. So I would call that homogenization. It's not perfect homogenization. It's probably within about 25%. But the neutrally buoyant dye, it ended up pretty well homogenized. Now, we ran experiments with heavy and light dye, and you could stratify the contaminants for sure, but we found that there was definitely mixing throughout the entire water column in either case. So I tried this in the field because I thought that was important to be able to do it in a model tank, in a numerical model, and then also in the field. At a site in New Jersey that wanted to collect samples at multiple depths to understand what was happening in the groundwater subsurface environment. Deployed snap samplers at 4 different depths in 2 different iterations. Once was just in the open well, and then another time we put what I call baffle device, or this plastic disc. Think of it as a coffee can lid that's placed in between each of the samplers, and you can see the difference in results. This is in parts per million for phenol, and concentrations were, pretty well homogenized in the open well. But when the baffles were placed in there, you ended up with about a 5 order of magnitude range. So that just putting this little disc in there prevented that mixing. You'll remember from 2 slides back with the mixing inhibitor device that was inserted in the model, basically the same thing would happen, is that you could limit that gravitation or that density mixing effect. So we have it in 3 different examples now: physical model, analytical or numerical, field tests. So it seems like we're pretty confident, I'd say, that number 1 never occurs. We never found that anywhere. It was impossible to see that occur in the field, in the models, and in the physical model. It is possible that number 2 could occur. We haven't seen that too much, where you'd have a high concentration and then 0, no concentration. But it theoretically is possible. What happened most was number 3, that you have some kind of mixing effect. It may not be perfect, and it might not be homogenized, but it will be, any contaminant entering the well will tend to mix vertically throughout the screen zone of the well. Number 4 can happen too if we have high enough density. Haven't seen it too many cases where you have absolute 0 concentration in one place and high in the other. What happens generally is you have a stratification that occurs. So, okay, so you can see that there's basically water flows through a well. It tends to mix. There's some dynamics to that we may not understand, but generally most wells tend to have a mixing effect. So how does pumping work? When we pump a well, isn't the same thing occurring? Yeah, pretty much. If you have, if you're pumping the well, then you're forcing that convection, or that water movement from the contaminated zone, the clean zone water, all moves within the well to the pump as you're pumping. And so instead of the entire well mixing over time, what happens is all of that mixing occurs right at the point of the pump intake and in the tubing that goes up to your discharge point. So no matter what the concentration is in the formation, eventually once you purge long enough, you will end up with a concentration that averages a flow-weighted average based on hydraulic conductivity of the aquifer and how much water is being generated through pumping. Okay, so how do we get to a flow-weighted average? Well, you have to pump long enough, really. Imagine the picture on the right here. Imagine the pump in the center. Think of flow lines. As you start pumping, the flow velocities are going to be fastest close to the pump because the flow is additive as you move from far away to the pump towards closer to the pump. Flow tends to go a little faster in the center of a pipe than it does in the edges. And so there are a handful of different calculations that Dr. Jamie Martin Hayden made in our SERDP study to figure out, how long does it take to actually purge a well. So in the axis here on the left, 1 means 100% well water, and 0 means 0% well water. Well, guess what? 3 to 5 well volumes gets you to the point where you have somewhere between 95 and 100% formation water and 0 screen water. Okay, does that jive? I guess that makes sense. If you purge 1 well volume, your more water is coming from close to the pump than far. You haven't had a chance for that water velocity to move all the way to the pump intake, so it takes a little while to actually clear the entire well. So at 1 well volume, you're depending on which assumption you make about the flow inside the pipe, you might be between 20 and maybe 40% screen zone water. Okay, so clearing time for the well really depends on two things: pumping rate, the well diameter, and the screen length. We do some quick estimations and say low flow sampling is typically at 250 mils per minute. You have a 10-foot well. How long does it take to pump one well volume? Well, calculate that out. It takes 23 minutes. So think of how long does it take for you to pump a 2-inch monitoring well and get to parameter stability? You know, maybe it's pretty commonly in the 20 to 40 minute range. That kind of jives with the, you don't necessarily need 3 to 5 well volumes to get parameter stability, because you're most of the way there to new formation. You might be at 80, 90% by the time you get to well volumes. So it kind of jives that parameter stability, you're not worrying about mixing from different zones. You're mostly getting formation water by a couple of well volumes. Now, be careful though. In a 4-inch well, that takes 94 minutes to get one well volume. So in a 4-inch well, low flow sampling, if you get parameter stability in less than 94 minutes, then you're probably sampling a lot of well water, and you may not even know it. Okay, here's another test study that we did as part of the SERDP project, little model, and this is really cool, and I'm glad that the model or the video works for me. It stopped for a couple of years there, and I got a new codec to make it work. But this model here is basically a screen zone of a well, so this is about 1 meter long. It's an axisymmetric model, in other words, so this is just a cross section through the well here on the left, and then an aquifer on the right. The blue represents clean water, and red represents dirty water. We assume that the initial condition was an average concentration of the whole thing, flow-weighted average, which comes out to be this point on this graph here. And then as you start to pump, water moves to the pump intake. I'll let it run a couple of times, and then I'll stop it so that you can, so I can screen through it a little bit, and you can see. Okay, so think about early in a purge. You're starting early in the purge. The first water to arrive to this pump, which is at the bottom here, is blue water, clean water, right? So this curve right here represents the discharge concentration during purging in that low zone. Okay, I'm not going to show 3 videos, but you can imagine if the pump intake was in the middle, you get this green curve, and if the pump intake was close to the source of contamination, that the concentration would actually increase early on. But as you purge more and more, you eventually get to an average concentration. And guess what? 3 to 5 well volumes, you start getting close to that average concentration. So so the takeaway here is that it's important that you choose the right place to put your pump. Most of the time you don't know. People pick the middle. You measure purge parameters to test this. Okay, so took this to the field. The SERDP project took this to the field. We tested this procedure by placing pumps and snap samplers in wells, which would allow us to collect samples before we started purging and after we started purging, above and below the pump intake. So we went out to the site, deployed snap samplers and pumps a couple of weeks in advance of sampling, went back to sample, collected the sample, the snap sample, we just snapped it, left everything in place, started purging. Purged for several hours to get to parameter stability and 3 to 5 well volumes, then snap the other snap samples. So notice here, this very much matches the curve I showed you in the last slide. So that early on, concentration changes, goes low, and then eventually it goes back to the average concentration. Starts about the same concentration that it ends. You have this divergence in the middle. What happened to the parameters during that period? Well, pH, as usual, hardly changed at all. ORP fluctuated a little bit, but the range was pretty narrow. DO was problematic, as it often is. We tapped the flow cell to make sure it was working properly, end up with a lot of variation. I don't have conductivity here shown, but it basically was flat too. The concern for me is that most of these changes are so small that most practitioners would say that's stable. ORP is not changing more than 3 or 4 or 5 from one to the next. Temperature is not changing. pH isn't changing. DO is squirrely. It's very common, and people would quit after 50 minutes, which would be at the furthest point from the initial concentration or the final concentration. So there is some concern that this is done correctly. And to avoid this kind of problem, you really have to pay attention to your field parameters and make sure they're not drifting. Okay, so the takeaway, it seems like not purging would be an appropriate way to collect samples in many wells. Passive equilibration is often very similar to the end-stage purging. Natural flow delivered to the well, ambient passive mixing. Just rely on that. Deploy your passive sampler in the well, allow the well to do the work. If you dedicate something like that, dedicate a snap sampler or other passive sampling device, always collect from the same place, it should be a very consistent way to collect samples. Avoid all of the effort associated with purging. And I'll talk about some of that and why that is an advantage. Okay, passive deployment considerations. How do you do this, actually? I mean, everyone's used to purging and going through the parameter stability and all of that. What do you have to do to deploy passive samplers? Well, you select the depth position based on your objective. Do you want to collect the closest sample to the water table? Do you want to collect a sample towards the bottom? Do you not know, and therefore the middle of the screen is a good a guess as any? Maybe you want vertical positioning. Maybe you want top and bottom. With passive sampling, you can definitely collect multiple levels, and that might be useful for your objective. Objective is the most important word there. Basically, it's pretty simple to do. Pre-deploy your sampling device ahead of time, typically 1 or 2 weeks, or it could be months in advance. Allow that time for the device to equilibrate with the well down hole. So that equilibration includes a disturbance. You want to get rid of the disturbance from inserting the device, and then let the device come to an equilibrium with the downhole dynamics. Come back to the site, collect that sample, and then redeploy your sampler, your new sampler, back downhole. So it's it's pretty simple. It's not very complicated to implement passive sampling. How do you select a method? Mainly it's based on analyte capability, but sometimes it can be sample volume too. It really depends on the method. Passive sampling is usually applicable, but not always. Sometimes if you truly need gallons of water for your analytical, then you might be stuck with purging. Okay, there are a handful of different classes of passive sampling systems. There are basically they're diffusion-based passive samplers. So you have a thin membrane that's polyethylene or regenerated cellulose, or it can even be a porous pipe that is filled with water, deployed into the well, and then a diffusion process occurs through that membrane. Different chemicals go through different membranes differently, so you can look that up and figure out which ones are appropriate for different analyte suites. But basically, the polyethylene is good for VOCs, most VOCs. Cellulose sampler can be used for additional analytes because the pore spaces are larger and not hydrophobic, so metals can go through a cellulose sampler, for example. Rigid porous pipe sampler, the holes are really big, so you can get all kinds of things, 1,4-dioxane or perchlorate, for example. There are grab-type samplers. A snap sampler is a grab sampler. A hydrosleeve, Kemmerer sampler, different types of samplers collect a whole water sample. So you won't be restricted in analyte type only in the volume that you can collect in the actual bottle. Then there's sorptive type samplers, a GOR or AGI sampler. It basically uses a sorbent material that's deployed down the well for a period of time, and then it's retrieved and contaminants desorbed and analyzed so you can calculate analyte mass. Okay, so which of these have gone through extensive prove-outs? Well, diffusion samplers have. Both the polyethylene or regenerated cellulose samplers have gone through USGS Air Force reports. ESTCP is a Department of Defense technology certification program. Regenerated cellulose has an ESTCP project and reports by the Navy, peer-reviewed literature. Snap samplers have also been through the ESTCP program, 5 different reports prepared by the Army Corps, and peer-reviewed literature. So there's a lot of backup information on those. GOR modular has also gone through the ESTCP. I'm not sure if there's peer-reviewed literature on that one. You'd have to explore that a little bit. I don't want to take too much time talking about all the individual methods, but I just wanted to make sure that you were aware of them individually. Specifically, the snap sampler, because I'm the snap sampler guy, I know more about that one than any of them. Just wanted to explain how it works. Basically, a snap sampler is a double-ended container. So there's a cap at either end of each of the bottles and a Teflon-coated spring in between. The bottles are loaded into a snap sampler. So the snap sampler is just a holder device that includes a release pin system. The release pin, the bottles are loaded in. They're different sized bottles. You have 40 mil VOA sized bottles and 125 or 350 mil poly bottles. Those are loaded into the snap samplers, and then those end caps are set into an open position. So both the top and the bottom are open, and you stack several of them in place. So you can stack up to 6 of them in a row. You can have multiples downhole. It's really up to you based on your analyte need and how many samples you need, how much water you need. A trigger line is attached. There's a pull trigger system that just basically operates this mousetrap. You pull on the trigger, it retracts those pins, that snaps the bottle shut. That's basically how it works. Lower the sampler down hole, lock it, leave it there for a period of time, come back and sample. So I think actually my next slide has my alliteration. So you load your samplers, you lower them down hole, you leave them, okay? Leave them for what might be a week, or it might be 6 months or a year or more. Return to the well, open it up, pull your trigger, or use air pressure. There's also an air-driven pneumatic trigger that snaps them shut. Retrieve them, prepare those bottles to go to the lab, reload new bottles, and then redeploy. So it's pretty simple. Load your samplers, lower down hole, leave. You return, retrieve your samplers, and then redeploy. That basic procedure is true for any passive sampler. This is just an example for the snap sampler. The big advantage for passive sampling in general is that you can sample by yourself. You don't need 2 people unless there's a health and safety reason for it. You don't need a giant truck. You truly can walk to the well with a backpack in most cases, or perhaps carrying a small cooler. Sampling in the woods is really convenient, and places where getting a large vehicle is difficult. You can sample with almost none of this equipment. You still might want to bring your cones if you're in traffic, but you don't need to have nearly the number of devices and amount of pre-preparation before sampling. Safety is improved. You won't have drums to move around. You won't have a generator. Won't have compressed gas. You won't have to handle fuel. And you'll spend a lot less time in the field because you're not dealing with nearly as much equipment. There are some differences amongst the passive methods. There have been studies that have been going on for the last at least 10 years trying to show the efficacy of passive sampling comparing to either volume-based purging or low-flow sampling. One of the first studies that was done at McClellan Air Force Base in California, where a multitude of passive samplers were compared to purge sampling. I'm going to show a couple of examples here just to give you an idea of what you can expect. Basically, one of these XY plots is a pretty common representation of a comparison between methods. On one axis, you'd have the passive sampling method, and a comparison on the other axis, you have the purge sampling method. Each one of these points represents the concentration at that well comparing the 2 different methods. When you have enough data points, you can generate a graph like this and run statistics to figure out what the slope of the line, so how good the recovery should get 1-to-1, and the scatter. How much scatter is there about that line? A higher number, close to 1, is better than a lower number. Okay, so if you're aiming for 1, that's good. You find a 1.04, that's pretty good. Having a little bit greater than 1 isn't so surprising for a snap sampler in particular because the bottles are closed and never poured at surface. So that 5% there is the difference between you having to actively pour a sample into a bottle. Oftentimes that's enough to lose a little bit. It's not significant. It's not going to really affect the decisions, but it is an indication that you know that you're getting everything there. If you look at some of these graphs, you can see that that correspondence is not too bad, and that's what a 90 correlation coefficient looks like. I put the diffusion bag sampler as an example. Tried to put it at the same scale. I know the dots are a little smaller, but I wanted to show that example of what a 60 correlation coefficient looks like. So you sort of have a bit more scatter about that 1-to-1 line, but it's not too bad. Okay, so there are differences. You don't want to add scatter. What you would hope to get, usually, is try to get a pretty good comparison where the results are, equally distributed above and below the line. So if you were to run some stats and calculate how many were above and below that line, you want the numbers to be equal. So in this case, we have about 100 points, a little more than 100 points comparing purge sampling to snap sampling, and we truncated the result above 500 just so that it would stay small and not get thrown off by the DNAPL wells. snap sampler is, whether the snap sampler is 2 times higher or the purge sample is 2 times higher. So that just gives me a sense of seeing that about 10% of them are different by a factor of 2. Okay, so you can't expect perfection. There is if you're purging a well or passive sampling a well, it's going to be different sometimes. What you want to see though is about equal numbers of above and below. That tells you that the differences are random. You can't have random differences just because when you're pumping, you might be pumping more from a high K zone, or maybe you put your pump at a position that's closer to the contamination, or maybe you're pulling water from above the screen or below the screen. Maybe that's the reason why there's a difference. But if it's truly random, you would expect that to occur fairly infrequently and equally in both directions. So in this case, there are 2 examples where there's an order of magnitude difference, and no time was the purge sample higher. You can see those order of magnitude differences, but generally you won't see too many. Other methods, this is sort of a clever device. The hydrosleeve is sort of a clever device that is sort of like, it's almost like an upside-down baler. Basically, you lower it down, and instead of filling on the way down, it fills on the way up. It seems to result in some noisier data, though. And so this is an example from this Patel report, reported this, showing quite a bit more scatter, and it seems to be more in one direction. So you've got, almost a third of them, I guess it's a little bit more than a third of them, that are lower by a factor of 2. And you can also just even tell by just eyeballing, you can see that the concentrations are on the low side of the curve. And a few more that are order of magnitude lower. Okay, so is that important? How important is that? Well, I think it's a little important because the error thing and how much variability there is really impacts how we make our decisions. I mean, ultimately, that's all we're doing. Is we're plotting a trend, looking at the database over time, and making decisions about whether our remedies are working. So if you have a perfect, simple declining trend, perfect, concentrations are declining over time, we superimpose our sampling method on that. If we have 30% random error, and this is just Excel, this isn't real data, that 24 sampling events kind of looks like that. If you add 10% random error, it kind of looks like that. You can see the difference, right? Maybe across both of these graphs, you could see that trend. But at any point in time, if you were halfway through that, it'd be a little harder to draw that. And it might be confusing to you, as you might be really happy right here during this quarter. Oh, we had great success, it's all cleaned up. But several quarters in a row, it's all going up. Start getting sad and nervous, and then happy and sad again. And so it would take, this whole 6 years before you could really draw that line. I would argue with 10% random error, you can see that trend much sooner, and it will help you make decisions. I think this is where the rubber hits the road with a method that's consistent. And I think that that's important. Independent of the cost savings of collecting samples, you want samples to improve your data quality, not degrade it. Okay, so here's an example of a site in California where they converted from purge sampling to snap sampling, about 50% improvement. And you can, eyeball, you can see that there's less variation. So that's just an example of one passive sampling method that does that for people. Okay, so the reason that we're all here oftentimes is because we're trying to improve cost. Purging requires more time in the field, have to have a lot of equipment, and generates waste. If we can avoid that, it's a bonus for everybody. Passive sampling allows you to sample right away, so that really solves that problem of collecting a lot of sample, bringing equipment to the site. So no more equipment rentals, no more pumping, no more troubleshooting, calibrating meters, measuring parameters, and generating waste and handling it. All of that takes half the time that you are collecting samples. If you can always sample right away, sample failure faster, know your sample, and improve data quality, all of those things are going to improve things for you. GSI Environmental completed an analysis of a handful of different sampling methods, including low-flow sampling, snap sampling, and that clever baler device, and found that, yes, the passive sampling methods were much less expensive than low-flow sampling. It's not that surprising. Pretty common, 50% savings. They also tested some other interesting alternatives to low-flow sampling, which could also save money too. I don't have time to talk about that now, but that's going to be coming out soon, and people will probably talk about that as an alternative to measuring parameters, but to rather collect an arbitrary volume instead. Those alternative methods, including snap sampling and the alternative purge methods, are pretty commonly 50% cost savers. And that's really the driver for people to want to go to passive sampling. Environmental sustainability, much less time in the field, fewer days in the field, fewer trips means less fuel, less solid waste, no purge water waste. All of those things are great benefits of passive sampling to help your sustainability and your footprint. The SNAP sampler in particular is manufactured with renewable energy. This picture of this wind turbine here is the facility that makes all the plastics for the SNAP sampler. So they actually have 2 wind turbines now. It's a place in upstate New York, so it's made in the United States, and generates, they have their no carbon footprint. So even their plastics that they buy, they make up for the carbon footprint with their wind turbine. SNAP samplers are reusable and come with a limited lifetime warranty. So you won't even have to replace them practically in a typical lifetime of a groundwater monitoring program. So in terms of environmental sustainability, all these methods are great, and it's really an improvement. And if you have a metric of sustainability, all of these will help you quite a bit. Okay, regulatory guides. I mentioned the ITRC guide. It's sort of an early one. It came out when things were new. It's very detailed, and it's a good one. It's a good one to read through. It includes a SNAP sampler, diffusion type samplers, sorptive samplers, hydrosleeve. Link right there if you'd have a look at it. More recently, the ASTM guide takes advantage of much of the prove-out work that's been done since 2007. This device only includes passive methods, truly passive methods, the way they defined it, which meant that the sample was in the container that was deployed at depth, so there's no movement of the container. So that would apply to the SNAP sampler because it doesn't move when it collects the sample, and the diffusion sampler because that doesn't move. The analytes diffuse into that sampler, and the same thing with the sorptive sampler. It stays in a fixed position. Things like a baler or a chemmer or hydrosleeve don't apply because you have to actually move it around, to deploy, or I guess a KBIS sampler too wouldn't count because it's not passive. You actively have to go and collect that sample. So there's a link to that. That costs money, unfortunately, but if your organization has access, you should be able to get a hold of the ASTM guide. Okay, so there's a lot of backup information, lots of information studies that show equivalence between methods, but you're still going to have an interaction with your regulator. I encourage you to talk to them. You have to ask them. Propose to use the method. That can either be in a telephone call or a letter, or putting the SOP in your sampling analysis plan. Ask for guidance. Ask them what they want. It's always good to have a positive interaction with your regulator. I also say ask for guidance, not like, Dad, where should I go to college? But it should be more like, can you make guidance for us? There's guidance for low-flow sampling. There's guidance for purge sampling. If there's guidance for passive sampling, it'll be much easier in the future. So if you're thinking about passive sampling, encourage your regulator to put together guidance for you. Different states have different levels of acceptance or of the different methods, and so hopefully your state either is open to it or will be open to it. It's sort of, I would say it's the wave of the future. It's been around for 10 years, and it's really going in that direction. Take advantage of the vendor SOPs. Oftentimes there's a detailed explanation. You can just staple it to the back or insert it electronically into your sampling analysis plan. Makes life much easier. If you need to provide site-specific data, convince your regulator, offer first to do a historical comparison. I think it's oftentimes if you can sample passively for 1 or 2 years and show that it's the data trends are similar and your data variability is similar, that might be okay. But be aware that you may have to do a side-by-side study. It's pretty common to do a side-by-side study. They're usually not terribly expensive, and they're usually also worth it. You may spend an extra event of doing double analysis, but in the end, the 50% cost savings that you're going to achieve is going to improve things so much that it'll be worth it. Okay, so just to to wrap up, technically wells normally flow through. Water is going to flow through the well. Passive sampling takes advantage of that well flow through and mixing, and lets you avoid purging. Results are normally very similar to low flow purging or low flow or 3-well volume purging. There can be outliers, there can be differences, but those differences ought to be equally distributed, higher or lower. So basically what that tells you is that your method is not biased. You just have some difference between the purge method and the no-purge method. There's really no one that can say which one is right. They're just different. And so the argument of logic can be the same, that there's an improvement to go to no-purge sampling for all of the sustainability and the cost arguments, and probably for data quality too. Low-flow sampling replaced volume purge sampling largely by an argument of logic. You're not going to be purging as much water. You're going to lower turbidity. It should be a better sample. So there's parallels between the conversion from bailing lots of water in wells to low-flow sampling, and then also from low-flow sampling to passive sampling. It's sort of a continuum, and I think that it's fair to say that that you should expect that passive sampling is going to increase in the future because of the economic benefits. There are several different methods and approaches. There are diffusion methods, grab methods, sorption methods. You can explore those and figure out what makes most sense for you. Cost savings is pretty substantial. 50%, as I was showing, is a good rule of thumb. Reducing waste, often purge water waste is reduced to 0. So sustainability is improved. Regulatory understanding and acceptance is growing, but it's really up to you. I mean, you're going to have to take it to them and make the case. There's plenty of information there that should help you. And I'll just go to that right now. There are papers and multitudes of reports and information available that can help you make the case. And any of the vendors can help you do that too. So what I'd like to do at this point then is to pass it back to Savannah. And I guess we're going to open up to some questions. And it looks like we still have a few minutes to do that before 1. And again, I really appreciate the opportunity to present. And I hope that I was yelling enough that you all could hear me. All right. What do you think?
All right. Thank you, Sandy. That was very informative. We have had several questions come in, so we'll try and get through as many as possible. The first one that we had was, let me see here. How much depends on correct installation of the well, for instance, correct installation of the filter pack? And this question was asked earlier in your presentation, so I'm not sure what slide you were on for this one.
Well, I think I can answer that. Of course, the well has to be reasonably installed. You can't have a completely plugged well. You can't have water that doesn't flow through the well. But I think that that's actually pretty rare for that to occur. I mean, the well has to be reasonably straight so you can get the equipment down the hole. I think, and maybe I'm reading into the question a little bit, but it sounds like you want to make sure that the water is actually exchanging in the well. And so in most wells, you know that because you've pumped it before. And if you pumped it before and you get a reasonable recovery, so in other words, you don't pump it and it goes dry and water never comes back or takes 3 weeks to come back. As long as water reasonably comes back, you can anticipate that there is hydraulic communication between inside and outside the well, and that water will move through. It may move through slower than it does in the aquifer if you've got a smeared filter pack or something, but it will exchange. If you're really curious and want to do your own experimentation, you can do dye tests, or you can add a chloride or even DI water and see how the concentration attenuates. So that can demonstrate to yourself that the water is flowing through. But really, there's few reasons why you'd expect it not to flow through.
Okay. Since the sample results with a passive sampler will be a flow-weighted average concentration representing the entire screen length of the well, what do you have to say about an ideal screen length when constructing a well? It seems short. 10 feet or less would be best? Question mark.
That's the magic question. I think you can't go too long. We didn't test long screen wells in our study to know whether they were all 10 feet, and some of them were 5 feet. So a 20-footer, I don't really know if that is appropriate. There are states that require that if you have longer screen wells that any passive sampling method you test for stratification. And that seems fair. I don't think you need to do the test every 5 feet. If you say you had a 20-foot well and you tested at 5 feet into it and 15 feet into it and the results are the same as each other, then maybe you don't have to worry about it. But I hesitate to say exactly what how long you can go. I kind of think, I'm a hydrogeologist. When I used to do that, I tried to make 5 and 10-foot wells just so that you weren't averaging too much of the aquifer. I think that those lengths are safe for passive sampling methods, but it really depends. Every well is going to be a little bit different, and so just like with low flow sampling and placing the pump, how do you decide to do that? Do you put it in the middle? I think probably most of the time, and no one ever checks to see if that's correct. I mean, maybe you could try that in top, middle, and bottom and get to results as well. So I'm not sure I can answer that perfectly for you. I hope that helps a little.
Okay, thank you. Can you provide comment on the application of passive sampling in wells screened across the water table and potential impacts of volatilization and enhanced biodegradation due to the presence of the air-water interface within the well screen?
Yeah, my experience is that it is not as big an influence as you would think. If you think that the the surface area of the water at the top of a 2-inch well is only the size that you can make with your fingers, a circle that you can make with your fingers, it's actually a pretty small surface area. And if water is exchanging, over the course of a day, how much is really being lost? How much oxygen is being introduced? It's something that is probably less than you think, and it's usually not a concern. But again, it's something that you can test if you are curious or interested. It also depends on what you're analyzing for. Some analytes are not really affected by presence of oxygen. Volatilization, I think, doesn't really occur. In water table wells that we've tested, we really don't see a statistical difference. I mean, we always see a snap sampler as being 5 or 10% high. So it never goes the other way where we're consistently low. So I mean, that's an anecdote, really, but that's kind of my thought on the water exposed to air, that it's not as big a problem as people worry about.
Okay, we are getting a lot of questions in, so I don't think we're going to get even through a quarter of them. So I'll just ask maybe.
Will you save them? Maybe I can. And do they come to us from a specific individual? Maybe I could answer them offline later.
Yes, definitely. And we'll we can. I guess everyone, if your question does not get answered, feel free to send an email to either Brad or Sandy, and which we have listed on a slide. Go ahead and send your questions that way so we can be sure to address all of your questions. We're not trying to leave you guys out at all. There are just a lot of questions coming in, which is very good. So let's see, let me find one more that I can ask. Okay, so this one is particular about the SNAP sampler. How shall we clean the plastic devices of the SNAP sampler at each sampling? Is it possible to clean, or shall we take to trash? Is it a concern?
Maybe I didn't explain that all super well, but the samplers themselves, the white part that you see, the white and blue part that you see that holds the bottle, is a dedicated piece of equipment. So that resides in the well and stays in the well from event to event. So typically, just like a dedicated pump, you would not decon that. So you retrieve it, you remove the bottles from the SNAP samplers. Those would get prepared and sent to the lab. Then you load new bottles into the samplers and then lower the whole business back down hole. So it's coming out of the well and going right back into the same well. As long as you protect it and keep it from getting dirty while it's out of the hole, put it on plastic or whatnot, then you shouldn't have to decon it. You might want to look at it, make sure it doesn't have any sand or grit or something that might interfere with the function, but you shouldn't have to clean it.
Okay, thank you. All right, another one about the snap sampler, and we'll finish it off with that. So, how do you collect a snap sample when you need to use a preservative?
Yeah, we have that information in our SOP. The preservative is added later. So there's a little cavity in the cap that allows you to add acid, and then there's a membrane to pierce, which will allow the acid to go into the snap sampler container, and then you screw septic caps on that so it's sealed and closed up and can go to the laboratory preserved. If you don't want to do the acid preservation in the field, then you don't have to. It just means that your hold time is a little shorter, but it can be done.
All right, great. That's a good question. So we'll go ahead and finish this out, and we appreciate everyone who has been in attendance. And like I said earlier, if your question did not get answered, we do have a list of who's asked that and your question, but I also highly recommend that you email either Brad with EOS Remediation or Sandy directly to ensure that your questions get answered. So thanks again, everyone, and we look forward to the next webinar in a couple months.
All right, very good. Thank you so much.
Thanks, Sandy.
All right, bye-bye then.